All right, let's dive into a science that's so fundamental, so absolutely critical, that without it, our entire modern world, I'm talking everything from a tiny watch on your wrist to a giant wind turbine, would just grind to a screeching, catastrophic halt. It's this invisible science, and it's constantly at work all around us. So what is this unseen force that keeps our world in motion? Let's find out.
You know, to really understand the hero of our story today, we first have to meet the villain. So what is it? What is this one invisible force that engineers have been battling since, well, since the very invention of the wheel?
You guessed it, friction. It is the universal bad guy in every single mechanical story. It's that constant resistance that just wears down parts, wastes an incredible amount of energy as heat, and is always trying to stop progress right in its tracks.
And let's be really clear about this enemy. Every single time two surfaces rub against each other, friction is there, causing wear and tear and generating heat. Now, in high-performance machinery, this isn't just some minor annoyance. No, it's a primary cause of failure and a massive drain on efficiency.
But you know how it goes. For every great villain, there's got to be a hero. And in this story, it's a concept we all think we know, at least on the surface. Lubrication, the slippery solution that seems so simple, but is actually incredibly complex.
So this is not just about making things oily. The entire science of lubrication is built around one single critical goal: creating and maintaining a protective film. A film that's thick enough to keep moving surfaces from ever actually touching. I mean, if they don't touch, they don't wear out. It's that simple and, well, that incredibly difficult. And here's where the basic magic happens. As one surface, let's say a rotating shaft, starts to move, it literally drags the lubricant along with it. This motion wedges the fluid into the gap, creating this immense pressure, what we call hydrodynamic pressure, that physically lifts the surfaces apart. They are literally floating on a microscopic layer of fluid. Amazing, right? But okay, here's the twist in the story. In the world of things like jet engines, massive wind turbines, or high-precision industrial robots, the pressures, the temperatures, and the speeds are just so extreme that this simple process gets pushed to its absolute breaking point. Think about it. Your car engine. Yeah, it operates under some pretty tough conditions. But a modern wind turbine bearing? It has to deal with immense, constantly shifting loads and just wild temperature swings. Even a tiny misalignment in a machine, something you could never see with the naked eye, can completely change the lubrication game and lead to catastrophic failure. So the crucial point here is that engineers today are basically fighting a war on multiple fronts. That protective film of lubricant, it can get squeezed so thin that it just breaks down. The friction can generate so much heat that the lubricant itself starts to fail. And in things like electric motors, get this, even electrical discharges can alter the fluid's properties. These are the really complex problems that modern lubrication science has to solve. So how in the world are engineers fighting back against all these complex problems? Well, they're not just pouring in some different kind of oil anymore. Oh no. They are engineering the lubricant and the surfaces themselves at an almost molecular level. This is some next-level stuff. This quote really gets to the heart of the challenge, doesn't it? We are talking about controlling a fluid that can be thinner than a soap bubble, but it has to be strong enough to support tons of force. The scale is just mind-boggling, and to control it, you need a brand new, very sophisticated toolkit. Researchers are basically attacking the problem from every possible angle. They're using complex mathematical models of fluid dynamics, I'm talking the same kind of math used to design airplanes, to predict exactly how a lubricant will flow under pressure. They're studying how solid metal surfaces actually bend and deform under that pressure. They are even designing microscopic patterns directly onto surfaces and inventing smart fluids that can change their properties on command. It's a full-on scientific assault. Okay, let's zoom in on this EHL thing because it is fascinating. The pressure in these tiny contact zones can get so extreme that it momentarily deforms the solid metal surfaces, creating a little pocket. At the exact same time, that immense pressure makes the lubricant act almost like a solid, which dramatically increases its ability to carry the load. It's kind of like a car hydroplaning on water, but in this case, it's controlled and perfectly engineered to happen millions of times a second. So how do they test all this? I mean, you can't just build a new billion-dollar jet engine to see if an oil works, right? That's where these incredibly powerful computer simulations come in. These complex models can predict everything from heat transfer to the effect of a single microscopic bump on a surface. It allows engineers to design and test thousands of solutions in the virtual world before they ever have to build a single physical part. Now, this is one of my favorite parts.
Instead of trying to make surfaces as smooth as possible, which is what you'd think, engineers are now intentionally adding microscopic patterns, things like dimples, grooves, even tiny wing shapes. It's just like how the dimples on a golf ball manipulate airflow. Well, these tiny textures control the lubricant's flow to generate more lift and more stability. The surface itself becomes an active, intelligent part of the whole system. Just incredible.
So, if maintaining this tiny, fragile film of lubricant is so challenging, what if we could just get rid of it altogether? The future of this field is looking at technologies that are completely rewriting the fundamental rules of the game.
So, first up, we have bearings that run on a cushion of air or another gas, totally oil-free and perfect for high-speed, clean applications. Then you've got systems that use an external pump to force pressurized fluid into the gap, lifting components before they even start moving to eliminate that damaging startup wear. And finally, you have what might be the ultimate solution, magnetic bearings. They use powerful computer-controlled magnetic fields to literally levitate a shaft in midair. We're talking no contact, no fluid, and virtually zero friction.
And the payoff for all this work? It's enormous. Just look at the dramatic reduction in energy that's wasted to friction. While a traditional bearing will always have some loss, these new technologies, especially magnetic bearings, get us incredibly close to a world of perfect, frictionless motion. The potential efficiency gains for our entire energy infrastructure, well, they're just massive.
So we end with this question. As we build faster, more powerful, and more efficient machines, it seems the real key to unlocking their potential isn't in the massive gears or the powerful engines, but in controlling the invisible, microscopic gaps between them. The biggest breakthroughs, it turns out, are truly hiding in the tiniest of spaces.